Well, I hope that you all are staying inside and keeping warm. And in the meantime here, we want to think deeply about something while you're staying inside and keeping warm, and that's the topic of infinity. And along with that is this idea of cardinality or counting. So today, I'm going to teach you how to count. So if I were just to, draw some geometric figures here, like, a triangle, and say a square and a circle, and I said, how many are there? You would tell me, well, there's 3 of them. Well, how do you know? How do you know there's 3 of them? Well, you can count them. 1, 2, 3. And that's the way you learned how to count when you were little. You took objects and you matched them up with the natural numbers starting at 1. And when you do that, you're actually doing a one-to-one correspondence between the figures here, that's supposed to be a double arrow, and the numerals, natural numbers here. So you're doing a one-to-one correspondence. So you're actually specifying a one-to-one onto function by counting 1, 2, 3, 4, etc. So we're going to generalize this idea to infinite sets. So we're going to define 2 sets to be equinumerous here, 2 sets s and t, if there is a one-to-one and onto function f that goes from s to t, or from t to s. It can go either way. And we'll write s is equinumerous with t, so we'll use a tilde, so equivalent. You sometimes say that s is equivalent to t. Notice that equinumerous is an equivalence relation on the family of sets. So, every set's equinumerous to itself. If s is equinumerous with t, then t is equinumerous with s. You just use the inverse function. And if s is equinumerous with t, which is equinumerous with another set r, and say this is, carried out by a one-to-one onto function f, and this is carried out by a one-to-one onto function g, then equinumerous from s to r is carried out by the composition g composition f. So it's equivalence relation. So that means that every equivalence relation defines a partition. So if you divide up all sets by their cardinality, by their size, all sets of the same size are in an equivalence class. So there's all the sets of size 1, all the sets of size 2, etc. for finite sets, and then also for infinite sets. And it turns out that there's actually different sizes of infinity. Well, let's first talk about what we mean here. So a finite set, S, is going to be something that's either the empty set or it's equinumerous with the first n natural numbers. So you can find a one-to-one onto function between the elements in S and the numbers 1, 2, 3 up to n. And then a set is infinite if it's not finite. So anything that you can't put in one-to-one correspondence with the first n natural numbers is infinite. Now, a special kind of infinite, the smallest kind of infinite, is what's called enumerable. And those are sets S that are equinumerous with the natural numbers. So the natural numbers are actually the smallest size of infinity. And then we say that a set S is countable if it's either finite or it's enumerable. So you can either put in one-to-one correspondence with 1 through n, or you can put in one-to-one correspondence with the natural numbers. And then infinities that are bigger than countable are called uncountable. So uncountable, not countable, that means you cannot put it in one-to-one correspondence with the natural numbers. So S is not equinumerous with your natural numbers. Okay, so if it's too big, you can't put it in one-to-one correspondence with the natural numbers. So we'll find out that sizes of infinity are kind of counterintuitive. So hopefully we're going to develop a little bit better intuition here as we go along and look at some examples. And I'm going to shorten this section up here because of the day or so that we missed because of snow or freezing cold. So the real numbers here, this is supposed to be script R. The real numbers are actually equinumerous with the positive real numbers. So the way that we would show that is we'd want some function f that goes from the real numbers onto the open interval 0 to infinity, so onto the positive reals, or vice versa. So we could go the other way too. And you just have to find one function that does this. So I'm going to consider our function f of x, defined by e to the x. Okay, so recall here that the domain of e to the x is all real numbers. So that's minus infinity to infinity. And then the range, remember, is just positives. So range e to the x is 0 to infinity. So we've got the right domain and range here. We just need to show that this guy is 1 to 1 and onto. Okay, so if we want to show this, we not only need to specify the function, but we need to show it's 1 to 1 and onto. So f is 1 to 1. So to show this, we need to start with two function values that are equal. So suppose that f of x1 equals f of x2. And we want to go backwards and show that x1 equals x2. So this is saying here that e to the x1 is equal to e to the x2. And then we can just take logs of both sides. So natural log of e to the x1 then has to equal the natural log of e to the x2. And then by cancellation laws, we get that x1 equals x2. Well, that's what it means to be 1 to 1. You start with f of x1 equals f of x2, and it had to be the case that x1 equals x2. So that part checks out. And what about onto? Okay, so f is onto, and we got to specify what set. So onto our range here. If we left that out, we mean onto the range. So how do we show that it's onto? Well, you got to pick a general element of your range. Okay, so let's let y be an element of the set that we're mapping onto, 0, infinity. And you got to find the thing that gets sent to y. And remember, the way that we did that before was by solving the equation for x in terms of y. So our f of x is e to the x, and we set that equal to y. And then if you take logs on both sides, natural log of e to the x is x, and natural log of y on the right hand side. So the natural log of y is the thing that you plug in and you get out y. So in other words, f of natural log of y is, well, f takes what you put in and exponentiates it. So we're doing e to the natural log of y, and that's cancellation law in the other order, and that gives you y. Okay, so therefore it's onto. So 1 to 1 onto, we conclude here then, therefore real numbers are equinumerous with the positive reals. So think about what this says. It's kind of cool. You take the real numbers, you throw half of them away. Okay, you throw away all the negatives, and what you got left is the same size. It's equinumerous, 1 to 1 correspondence to what you started with. So you throw half of infinity away and you still got as much stuff left. So that's kind of counterintuitive. Second example, if you look at the integers, they're actually equinumerous with the natural numbers. And there's actually a few ways that you can show this. So think about what this is saying again. The integers, this is positive and negative natural numbers, and if you throw away the negatives, you still got as much left as what you started with. So the natural numbers, just the positive integers, are the same size as all the integers. So what do we do here? Well, we've got to find a 1 to 1 onto function here. So we've got to find a 1 to 1 onto f that goes one way or the other. I will go from z to n, okay, from the integers to the natural numbers. And the idea, what we're going to do is we are going to map the positive integers onto the even naturals. Okay, so onto the evens. And then we're going to map 0 and the negatives onto the odds. So z minus is going to go onto the odds. So that's how we're going to divide that up. Okay, so I'm going to specify the function. It is actually a piecewise function, and it's defined by, I'm going to use n instead of x here, because we're talking about whole numbers. Well, we're talking about integers, I'm sorry. So f of n is going to be 2n if n is greater than or equal to 1. Okay, so if you've got the positives, they go on to 2n, which is an even. And then it's going to go on to negative 2n plus 1. And that's going to be if n is less than or equal 0. So the negative 2n would be, see, n is negative, so negative 2n would be positive and even, and then you add 1 and it offsets it to an odd. So if you look at this, it's actually going to be one-to-one and onto by construction. Okay, here it's pretty easy to see that it's one-to-one and onto. If you've got different natural numbers here, they get sent to different evens. If n1 is not equal to n2, then 2n1 is not equal to 2n2, and then the same thing with your odds. Now, if you lay out the integers here, you can kind of see how this gets mapped. So let's see, we got 0 in the middle, and we got 1, 2, 3 positives, and then we got negative 1, negative 2, negative 3, and then I'm going to lay out the natural numbers underneath, and those are 1, 2, 3, 4, etc. And then the way that we're going to match these guys up, do our one-to-one, is, okay, n greater than or equal 1, you map to twice the number. So 1 is going to 2, and then 2 is going to 4, 2, 5, 6, so 3 is going to 6, etc. So each number goes to twice the number. And then for the odd ones, okay, so for the negatives, they go to the odds. So negative 2 times 0 is 0, plus 1 is 1, so 0 goes to 1. Plug a negative 1 in here. Negative 2 times negative 1 is positive 2, plus 1 is 3, so that negative 1 is going to 3. Plug a negative 2 in, times negative 2 is positive 4, plus 1 is 5. Okay, so sky is going to 5, and so on. So you can see here that everything gets hit, it's onto, and different things up here go to different things down here. So you can see pretty clearly that's one-to-one and onto. So the natural numbers and the integers, same size. Okay, we threw away half of it, but we still got just as much left because we can still, put things in one-to-one correspondence with the natural numbers. Now, both of these examples are illustrating an interesting property that's only true of infinite sets, and that is that infinite sets are the same size as a proper subset of themselves. So we took this infinite set, we threw some stuff away, and it was still equinumerous with a subset of itself. Actually half of itself, and did the same thing with the reals. They were equinumerous with only half the reals. And this is really interesting. Only happens for infinite sets. You can't do that with a finite set. If you throw something away, it's strictly smaller. Okay, doesn't happen with infinite sets. And this actually plays into the idea of Hilbert's hotel. So Hilbert is a mathematician. So Hilbert's hotel. Okay, so Hilbert's hotel has an infinite number of rooms, and the number of rooms are numbered, 1, 2, 3, 4, etc. Okay, they've got natural numbers on the doors, infinitely many. And, a whole bunch of, mathematicians come in for a convention, infinite number, okay, and they say, we'd like a room. And Hilbert says, well, that's great. We can accommodate all you guys. We'll put the first person in, room number 1, the next person that comes in room number 2, room number 3, etc. Okay? We got you covered. Okay, but, then later that night, another group of mathematicians comes in, an infinite number. And they say, hey, you got any room for us? He says, well, we're full. Every room's taken, but sure, we've got room for an infinite number more guests. Okay, what we're going to do is we're going to take every guest and we're going to shift them to the room number that's twice their number. So guest number 1 is going to go to room 2. Guest number 2 is going to go to room 4. Actually, let me do this. Okay, let me line them up a different way. Give myself a little bit more room here. There we go. Okay, so here I'm going to tell you how we're going to move the guests around. Okay, so person number 1, we're going to send them to room 2. Person that's in room 2, we're sending them to room 4. Put on a couple extra numbers here. Person that's in room 3, we're going to send them to room 6. Do that all the way down the line. So then what rooms are empty? 1, 3, 5, 7, etc. and keeps going on. Oh, now we got infinitely many rooms available. Come on in, guys. We can accommodate infinitely more as long as it's a countable infinite. Okay, as long as you can list the people, they can come up to the counter one at a time. That's Hilbert's hotel. We got plenty of room for everybody. It's really counterintuitive. You could blow some brain cells thinking about that. So one important property of countable sets is that sets are countable if and only if the elements in the set can be listed. Okay, and this is a super important lemma. This comes up, just over and over in equinumerous problems, and it's a very important idea. And this one I would like to prove. So sets countable, we're going to assume it's countable and then show it can be listed. Do that one first, and then the converse. So let's let S be a countable set. And I'm going to abbreviate countable here. Okay, so let's let S be countable. Okay, then what's that mean? Well, S is finite ordered enumerable, because that's what countable means. So finite ordered enumerable. And then if S is finite, then it's equinumerous with 1 through n for some n. Okay, so if S is finite, then that implies that S is equinumerous with 1, 2, up to n for some n natural number. And that's by definition. And then that means that we can list. Oh, and this is so this means that we have a one-to-one onto function. Okay, so there exists an f that goes from S into 1 through n, or actually the other way. I'm going to do the other way. We can do it either way. So from 1 to up to n into the set S, and it's 1-to-1 onto. That's definition of equinumerous. So then that means that we can list out the function values. So we can list f of 1, f of 2, all the way out to f of n. And in fact, these are going to be all the elements that are in S. Okay, so these are all the elements of that set S. Okay, because it's one-to-one onto function. So then if that's the case, then we'll just define, so we'll let S sub k equal f of k. And we'll do that for k equals 1 through n. And then that means that we can list our set. S is just going to be the set S1, which is f of 1, S2, f of 2, all the way up to S sub n, which is f of n. Okay, so we can list the elements. So that's the finite case. So now what's the other case? Well, it's denumerable. Okay, so if S is denumerable, then what's that mean? Well, that means that we can put it in one-to-one correspondence with the natural numbers. Okay, so then S is going to be equinumerous with the natural numbers, and that means that there exists a function f that goes from the natural numbers onto that set S. Okay, it's one-to-one and onto. And we can do the same thing with that. Okay, we can list the function values. Okay, so we can list f of 1, f of 2, f of 3, etc. Okay, we keep going, and we can do that for every natural number n, and these are going to be all the elements of S. And then we can do the same trick that we did before. We'll define S sub k to be f of k, and then we can list our set S is going to be S1, which is f of 1, S sub 2, which is f of 2, S sub 3, f of 3, etc. Okay, so if we kept going, we could list everything in the set. Okay, so that gets the forward direction. Conversely, okay, so for the converse, we're going to suppose that S can be listed. So if S can be listed, then we could write, say S equals S1, S2, ... Maybe finite, maybe infinite. Okay, so if it's finite, that's the easier case. So let's consider the denumerable case. So then what we're going to do is we want to show that it's countable, which means finite or denumerable. Okay, we assume it can be listed. So then we can define our function, define a one-to-one onto function. So we can define an f that goes, in this case, let's see here, I'll do f from the natural numbers into the set. Or this could be subset the natural numbers, first n natural numbers. And we're going to define that by f of n is going to be S sub n. Okay, then this thing is going to be one-to-one and onto by construction, right? Okay, if you if you start with two different natural numbers here, then you get two different elements in the set, right? 1 is not equal to 2, S1 is not equal to S2. These are distinct elements, okay? And everything in the set gets covered if you tell me which element you want here, S sub 2010, well, it gets paired up with the number 2010. So it's pretty clearly one-to-one and onto by construction. So F is one-to-one onto by construction. And so your set S is going to be countable, finite or denumerable. In this case, I did denumerable. We could do the same thing with the first finite number of natural numbers. So I'm going to say S is countable. So anytime you're almost any problem, you're going to be taking advantage of this. If something's countable, if you're doing a problem that involves a countable set, you're going to need to list it, and that's going to help your proof go easier. Because a lot of times what you want to do is you want to line elements up like this and try and decide what your function is by telling where things are going to go. Now the next theorem, it kind of makes sense that it should be true, and the proof actually is pretty involved. I'm going to skip this proof for sake of time because we are a little bit short with our snow day missed on Monday. So, but this theorem says if you start with a countable set and then you take a subset of that countable set, so T is a subset of S, then T also has to be countable. And that kind of makes sense. And the main idea is that if you've got this one-to-one onto function from the natural numbers into S, you just restrict it and you'll have a one-to-one onto function from the natural numbers to T. So it involves restricting your function. So that's one of the key ideas here. So it involves restricting F. Your F, which is one-to-one and onto. Because if you restrict a one-to-one onto function to a smaller domain, it'll still be one-to-one and onto. So now I want to illustrate this proof technique here of matching and using the fact that something is countable if and only if it can be listed with the idea of matching. So example 3 here says that if you take a subset A that's infinite and then B is a finite set, then A union B is equinumerous with, let's see, I think that should be A. Let's see, A is infinite, B is finite. Yeah, that should be A. A union B is equinumerous with A. So in other words, if you take an infinite set and you add on a finite number of elements, you haven't changed the size. It's not a different size of infinity. So, and what we want to do here is we'll start with the general infinite set A and let B be a finite set. So since A is infinite, it contains some denumerable subset. We're going to call that C. And the way that you can find that denumerable subset, I think they have you do this in the homework problems, is you do it by selection. So you select the first element of C. It's an infinite set. A is an infinite set, so there's infinitely many things left. So then you can select another element out of A and let that be the second element of C. And then you've only taken 2 things out. There's infinitely many left, so you can select a third element of C, and you construct your infinite set like that, inductively. But what we're going to do is we're going to look at the set A minus C. Okay, so this is the whole infinite set, and we've taken out this denumerable subset. And then here it is. Okay, so take A minus C, union B, and we're going to show that's equinumerous with A minus C, union C. Okay, so what we got to do is we got to match up these parts here. The denumerable plus finite is the same size as the denumerable set, and then these parts match up with the identity function. So if you can match things up in one-to-one correspondence, then they're the same size. Okay. So, well, what we know is that since C is this enumerable subset, that's countable. So you can list the elements in C. So let C be C1, C2, C3, etc. And then B is a finite set. So you can list the things that are in B. So let those be B1, B2 up to Bn. That ends at Bn there. For some n natural number. And then we're going to match pieces up. Okay, so first let's work on matching C union B with C. Okay, so we're going to match this piece with this piece in one-to-one correspondence, and then these two pieces will match up with the identity function. So C union B, we're going to list the elements out in that set. Okay, we're going to list the elements of B first, B1, B2, up to Bn. And then we're going to list the elements of C after that. C1, C2, C3, etc. So that's the elements of C union B, and then the elements of C are going to be C1, C2, etc. And then we're going to go out to, this will be C sub n, and then C sub n plus 1, and then keep going. So we can list the elements of B union C, we can list the elements of C, and then I got to tell you how to specify your one-to-one onto function. Well, just do it like this. Match B1 up with C1, B2 with C2, all the way up to Bn goes to Cn, and then C1 to C3, what's left over there, shift it. N numbers. So C1 goes to n plus 1, C2 goes to Cn plus 2, C3 goes to Cn plus 3, etc. Okay, and that's going to be one-to-one and onto by construction. So that part's one-to-one and onto. And then these pieces, A minus C, they get matched up with the identity function, which is one-to-one and onto. And that shows that they're equinumerous. So this part of the matching, that's really the important part that I want you to see out of this proof. Because a lot of the homework problems, you list out the sets and then decide how can you match them up. So you match them in one-to-one correspondence, they are the same size. They're equinumerous. So I really want to specify this function in a more formal way. It's nice to just, draw the arrows and say, okay, well, I know what to do, but let's actually, state what our function is. So we are going to define f, and this function is going to go from A minus C union C union B onto A minus C union C. Okay, and I am going to define in the first portion here, A minus C to A minus C. There, f of A is just going to equal A. Okay, and that's for A, an element of A minus C. And then the B's are going to get matched up with the first n C's. So f of B sub k is going to equal C sub k. And that is going to be for k equals 1 to n. And then the last portion, so that matches up our B's with the first part of the C's. And then the last portion is these guys here. And then the first n C's are already taken, so f of C sub k is going to get matched up with n plus k. So it's going to be C sub n plus k. And that's going to be for all natural numbers. So for k, an element of n. Okay, so there's our piecewise. It's actually piecewise function. I just wrote out 3 lines instead of f equals because I'm changing the symbol that I'm inputting here. I'm not using just an x. So this f here is 1 to 1 because each piece is. So it's pretty clear to see, well, the identity function here, that's always 1 to 1. Different input, different output. This piece is 1 to 1. Different B's get matched to different C's, and same thing here. Different C's, you shift them by n, they get matched up with different outputs. And then it's also onto. You can see that it's onto by construction. So it's 1 to 1 and onto because each piece is. And then all the sets are disjoint. The sets here on this side, they're all disjoint. Okay, so it's 1 to 1 because each piece is. It's onto. Since A minus C, comma, C, and B are disjoint. And each one of those subfunctions is onto. Okay, and then that finishes our proof. So that shows that A union B is equinumerous with A because we specified our 1-to-1 onto function. So this example has kind of one extra step to more than most of the problems that you'll do in homework. In homework, you'll probably be doing just like this much of it most of the time. You just be looking at, if you add on a finite number of things, or even if you add on a denumerable number of things, you can match it up and show it's the same size of infinity. And you would just be using this here. And you wouldn't have to worry about, breaking off and looking at the A minus C portion. Okay, so hopefully this gives you a good introduction to sizes of infinity. We will look at some more examples when we get back on Friday. So you're just working on finishing up the Section 7 homework, and I will see you then.